think so too.
I have a pencil marker.
There was a bunch of them in the physics lab that one day.
It's kind of circular.
Yeah, we must have some. If you come by the office, I'll look in the storeroom for you, or you can ask one of the office assistants.
My lab's like right after this and it's on the second floor. And also, I would like to get my textbook.
I used to have a little bit of.
How did I do, by the way?
Very well.
The K one, did I do that right? Or should I?
You got just about everything. I don't remember specifically.
Okay. Like, that's the only one where I was not 100% sure if I did, but I felt confident, so.
I don't remember probably. Okay, we've got great new stuff to talk about today. We're going to be breaking open a big new topic. We've spent the first bit of our semester here basically making sure we're familiar with all of the basic functions and manipulations. And we're going to start now discussing vectors. And we've already done a good bit of groundwork laying for this discussion, talking about force diagrams and free body diagrams and taking components of forces, for example. Super. Thank you very much. And I've got a few additional book chapters to hand you as well. Okay, so in our discussion of vectors, we're going to be generalizing and expressing a notational formalism for this idea, which we've already kind of hit on with respect to taking components of vectors.
Vectorious.
Let's start out by spending a couple minutes talking about basic notation. For starters, we'll write vectors with a little arrow sign on top of them. Very often, they'll be written just with a bar on top of them, and we get a little lazy and don't always explicitly write the arrow. But if I ever leave the little arrowhead off, I don't mean anything by it, just the bar is sufficient to denote your vector. In textbooks, very often vectors are denoted with bold type, so you might also sometimes keep your eye out for that. Sometimes they'll use a bold font to indicate a vector in lieu of a bar. Sometimes you might see both. The notation is going to be like this. If we have a vector has a magnitude and a direction. Now, that's not exactly the definition of a vector. We'll be a little bit more specific as we get a bit farther along, but those are essential properties of a vector. A magnitude, how long is the vector in some sense, and in what direction is it pointing. And in three-dimensional space, we'll have three components. For example, if we're using a normal XYZ, the vocabulary is Cartesian coordinate system, our vectors will have X components, Y components, and Z components. This is the way that we'll denote that on paper. This is the X component of the vector V, and that component points along the X direction. The Y component of the vector V points along the Y direction. And the Z component of the vector V points along the Z direction. These things are the components, or the coefficients. They're just numbers, possibly numbers in some unit system with dimensionality too. These these are the directions. You might call them the basis directions. So we have three directions that form a so-called basis for our vector space. And then any vector within that space can be described by its projections or its components along each of those basis vectors. Another word for these directions, which is very important, is unit vectors. In this case, the word unit means something very specific. It doesn't mean like units of. Do you know what unit means in this case? No.
Oh, length?
It has something to say about the length. It says that the length is
1.
1. Unit, unitary, one, a unit. It's a way of saying 1. So we've said that vectors have two properties, right? Vectors have a magnitude and they have a direction. And we denote vectors with little arrows on top. But there's a special kind of subcategory of vectors. The subcategory of vectors are the vectors that have length 1, the most vanilla length, the most plain, ordinary, uninteresting length. We denote them with a little different symbol. We put a hat on top. That's literally what we call it. It's a caret. It's the name of the symbol. We actually call it a hat. So in English, when we see that symbol, we'll usually either say out loud X hat or the X direction. And that's a recognition of the fact that if it has the most vanilla length, the thing that's significant about it is its directionality. Once again, we think of these things as a basis. There's a lot of kind of important vocabulary going on here. I'm trying to say things several different ways. All of this vocabulary is used very commonly. We think of them as a basis. How so? Well, they have certain properties. Again, our basis tends to be defined out of unit vectors. Vectors that have magnitude 1, where the thing has just direction as the relevant information is trying to convey. We have enough basis vectors to span the space. If it's a three-dimensional space, how many unit vectors do we need? 3. And whenever we can do so, which is almost always, it's convenient to make sure that our 3 unit vectors are independent from each other, that they point sideways to each other, they're perpendicular. The vocabulary is that they're orthogonal to each other. They're independent, they don't overlap with each other. So we formed our basis out of the most vanilla vectors, the unit 1, length 1 unit vectors, pointing along our 3 axes. And then any other vector in general can be expressed as, well, how much are you pointing along the x direction? How much are you pointing along the y direction? And how much are you pointing along the z direction? Makes sense to people? Notation, they're good. Now let me warn you about one thing. There's competing notation here that you'll see very often. This is the IJK notation. Don't be confused about it. It's the most simple thing. Some of us like to write x direction, y direction, z direction. Some people don't like to write x, y, z for fear of getting it confused with the variable itself, let's say. This is not the x variable, it's the x direction. So instead of x, y, z, sometimes people say I, j, k.
My experience, the IJK seems to be more relevant whenever you're talking about numbers specifically versus like graphically.
I don't think that's generally true. There are different communities of people that probably prefer one over the other. We're going to use the XYZ, but just keep your eye out. You'll often see IJ and K. So just mentally in your mind, if you see an I hat, turn it into an X hat. Or if you want to turn your X hats into I hats, or just understand that they're both the same thing. That's all there is to that. Let's talk for just a second about adding vectors. Adding vectors is very intuitive and simple. The phrase that's usually used, which I would suspect probably you've heard before. You heard that before, tip to tail? So we actually did a problem that was designed to sort of spur this thinking a little bit. We did it a little while ago, and we interpreted it then just as a trig problem, but it was already vector addition is really what it was. Do you remember a little while back we said, and then we're going to walk north for a little while, our hikers are walking some distance, and maybe they walk like this for a little while, and then maybe they walk like that for a little while, you know, whatever. So there were 3 vectors there, right? And then the question is, at the end of the day, how far are they away from the place that they started? And you remember basically what our approach to this was. We set up a coordinate system. You could call it north, south, east, west. You could call it just x and y in the usual way. And this vector, we said, well, that looks like it's intended to be 100% y, which is the way that I meant it. We just leave that be. But these others are both a little bit of x and a little bit of y, right? So what did we do? We took components as our vocabulary. We broke the thing up into components. We projected it along the basis directions would be another way to express that vocabulary. This strip is equivalent to that, followed by this. You might be a little more tired if you go that way, but in terms of where you end up, it's equivalent. This strip is equivalent to that and that. And of course, we put our arrowheads down, always making sure that the original complete trip is the hypotenuse of the triangle, that the components line up with our basis directions, and that the arrows are aligned such that the 2 segments really are identical to the same segment. So then, for example, if we had some angles defined here as such, say theta A and theta B, we could represent each of these sides here as magnitudes. So for example, if we call that L1, L2, and L3. This length would be L2, which trig function? Cosine, yeah, it's close to the angle there. Cos theta A. This one, that's opposite from the angle. That's right, that would be L2 sine theta A. This one, which one is that again?
Cosine.
Cosine is close to the angle, good. So L3 cos theta B, and this one, L3 sine theta B. And we followed our normal convention of trying to use acute angles less than 90 degrees to label things when possible. And just writing down magnitudes next to each of these arrows. The arrows now we think of course, as vectors. And we're going to add our vectors up. Our total path is L1 plus L2 plus L3. We could write it like that, right? And we could also write it as such. we could write it as L1x plus L2x plus L3x. That's right. Along the x direction, plus L1y and L2y and L3y. Along the y direction. And the very convenient thing about breaking these things up into their components along the basis directions is that at the end of the day, we have the length of this total vector that's the total vector, right? From the total start to the total finish. And we have its components broken up into its x part and its y part. So if need be, then we can find its magnitude very easily using the Pythagorean theorem. We can find its angle very easily using the inverse tangent.
So the way you set it up makes it look like the first formula you're trying to figure out the length traveled, but the second formula using vectors is trying to find the location that it ends up.
All I really want to convey with that is that these two notations are equivalent to each other.
What is L1 then? Is that the vector length or is it the vector position?
Since I've written it as a vector, what I mean by it is the total original arrow. And what I mean by L2 vector is that total arrow.
It's a magnitude, right?
Well, it's a magnitude and a direction.
Okay.
I'm not adding their magnitudes, I'm adding their vectors.
Okay.
So the fact that I've got the symbol on top should be indicating that I mean to add the vectors. And then this. So let's say that again, that's very important. What I'm saying in that equation is that this vector, which I've called L, is the same as this vector followed by that vector followed by this vector. And I've added them together, tip to tail, tip to tail. Just one displacement right after the other. I did this, I did that.
So how do we find the new L connecting our points?
How do we find the new L connecting the points? The most convenient way to do it usually is by breaking it up into components. So let's do that. So this new L connecting our points from the start to the end, well, we should add together all of the motion along the x direction that our three little vectors did individually. And we should add together all of the y motion that our three little vectors did individually. So let's do that explicitly now. So I'm just going to carry this equals over, and these things are all literally still equal to each other. Let's explicitly now, I need a little more room than that. Let's explicitly now combine together our x parts and our y parts. So L1 doesn't look like it has any x actually, right? It's 100%. It's 100% y. So I'm going to write 0 for x and all of L1 for y. Now, I want you to notice something here. Here, I've not written an arrow on top, right? If I don't write the arrow on top, I mean just the magnitude of the thing, not its direction. So I'm saying all of the magnitude of L1 is projected along the y direction. Now let's do L2. L2 has an x bit which is positive or negative, and a y bit which is negative. And when we pull this off of the diagram that's got the arrows and plug it into an equation where we don't have the arrows, we better bring the minus sign with us if it's either pointed down or left. So let's pick that off as the x bit, plus L2, which I now mean magnitude of L2, times cos theta A. And then this L2 sine theta, which is itself a positive magnitude, but it's oriented down. I'm going to write minus L2. So why don't you fill in, please, those last two spots there and there, reading off the diagram, and then let's check in just a second. Let's check ourselves. It looks to me like the y part here is down, right? So let's pick up that L3 cos theta b and make sure it's down. And then for the x cross, let's pick up that L3 sine theta b. Make sure it's negative. Now, let's put some numbers into this thing just to make it one bit more concrete here. And to the extent that I'm able, let's try to do this to scale so that it should correspond reasonably well with our expectations in scale for the final total. Into inch units, let's say. What I've done on the board. I've got a length of 13 for L1. And again, since I don't have any decoration on the top, I don't mean the vector, I just mean the magnitude. Another way to write that, it's even more explicit, is with vertical bars there, absolute value bars. If you see the absolute value bars, sometimes you'll even see this. If you see the absolute value bars, it's telling you the absolute value of the vector, meaning its magnitude. And that's trying to be like super explicit. I don't mean the vector, I mean its length. But also very often what you'll see is that just leaving the arrow off also implies that you. This one here is pretty similar to each other. That 14 maybe. And this one here, let's make that 19. Okay. And theta A and theta B, let's see, that's 45. Let's make that 22 degrees. That's pretty close. 19 degrees to make it just a little something different. So this over here, I'm going to continue the equals. All of these things following all the way through are literally equal to each other. Except now we're going to have, an absolutely concrete number to stick in front of the x hat. And likewise with the y hat. So let's run those through our calculators real quickly. The x hat. that number there?
6.79.
Anyone agree with that? Get something different? Agree? Okay. Let's check this one here.
Got negative 10.21.
Yeah.
Wait a second, make sure you got the same thing. Any questions, Courtney?
No, I'm just trying to figure out how to put in the calculator.
Okay, let's make sure we put it in the calculator. Okay, so walk through me with this. So let's make sure our calculator's clear. Make sure it's all clear. And then let's start off typing. 14 cos 22. And then you might have to put a parenthesis there to close out the cos. Okay. Minus 19 sine 19. You might put a parenthesis there to close out. Can you get the match there?
Yeah.
Let's see if that matches up at all with what we drew.
Surprising.
That's a little shorter.
Then,
I think I made that angle, I drew it a little bigger than 19. Probably.
seems like that came out pretty good.
It's 4-ish, and we said 7. It's not completely crazy. And then down, how far down are we? That's about 10, that was right on. Sorry. Now, let's finally calculate a magnitude and a direction. Let's call this angle alpha, if you like. Give it a name. And I'm going to call this angle beta. Now let's ask the question like this, like it might be asked in a word problem, let's say. What is the direction of the total displacement in degrees counterclockwise from the x direction? And if this were a word problem, you know, it might say, I measured in inches, but maybe these are hikers and they're miles. Okay? If I say a hiker walked north for 13 miles, these are enthusiastic people. Maybe make it kilometers.
Yeah, that's a little bit manageable.
A little bit more manageable. 14 kilometers at 22 degrees south of east. And then an additional 19 kilometers at 19 degrees west of south. And then the question could be, how far are they away from the starting point? How far are they away from camp? That's magnitude of the L vector. And in what direction is their total displacement in degrees counterclockwise from east or from x? So we're asking for alpha. Now again though, alpha is not an acute angle. I will suggest not trying to calculate alpha directly. I'll suggest defining instead and always putting it on the diagram so it's real clear what you're talking about. Let's define another angle beta, and we'll just take 360 minus beta when we're done. So beta is going to be, which trig function is good to use here? Arctangent. Arctangent or inverse tangent. And for tangent, which two sides of the triangle are we relating? Opposite over adjacent. Now, in this case, that's a positive and that's a negative, but we're not going to write down pluses and minuses, right? We're treating those as magnitudes, lengths of the side of a triangle, which are intrinsically positive. And I'm just trying to figure out what this angle is relative to lengths of the sides of a triangle, which are intrinsically positive. So relative to that angle beta, my opposite side should be what? 10.2. And relative to beta, my adjacent side, my close side, should be the 6.7. Let's take the arctangent of that ratio.
56.35. That's the rounded version.
Okay. Sure. And then finally, if we want alpha, let's just take that as 360 minus beta. What do we do that? 300 point.
303.
Oh, couldn't know that in our head. Are we track with that?
Yeah.
And finally, the word problem might ask, how far are they away from camp? In this case, we're looking for magnitude L. We can also write it like that. And what's the best way to get magnitude L? Pythagorean theorem. So we're going to say square root. Now I'm going to write something here in a way that I will not suggest doing. We take square root 6.79 squared and square root negative 10.2. I want to have just a few words about that negative sign. In some sense, the negative sign belongs there. In some sense. But it should be obvious to everyone that squaring it is going to cause the negative to go away, right? This is a very common place to make mistakes in your calculator. Because very commonly what people will type into their calculator is 6.79 squared minus 10.2 squared. But what happens is that that square binds more tightly in order of operations than the negative does. So you square the thing and then subtract it, which is not what you want at all. In this case, it would give you a negative number under the radical, which would scream at you, you've got an imaginary number, which you know that should be a major sign to go back and check your work. In addition, we've got a diagram here, which should be 12 or 11 something.
12.25.
So we had the fact that we had the diagram to check ourselves a little bit and see if that's something that's reasonable. Does that make good sense to everybody? That's adding vectors. Just one more time here through the diagram. Make sure 100% that's clear. What did we do? Well, we added up all our x parts. This didn't give us anything. That gave us an x. And that took away some x. So our total x was that. Our y parts. The first step gave us some y. The second step took away some y. And the third step took away even more y. So that we ended up with that much negative. So we combined our x parts together. Along the x direction. Combined our y parts along the y direction. And we ended up with a vector like any other. And we get its magnitude with the Pythagorean theorem. And we get its directionality using the inverse. That's pretty common type of calculation needed in all types of applications all over the place. The next thing I want to talk about for just half a second, because in reality it's no different from what we've done already, is subtracting vectors. Well, you guys learned somewhere along first or second grade that subtraction is the same as adding a negative. What would you imagine the negative of a vector would mean in graphical sense? If I have an arrow, negative means, yeah, put the arrow on the other side, right? So subtracting vectors means nothing other than adding the negative. And what negative means is split the arrow. So I suspect that means probably exactly what you think. Nothing very tricky.
When you say arrow, you mean flip the vector?
Flip the vector on which side does the arrow head appear? So for example, if V1 was this, okay, and V2 was that, then you could draw little pictures representing our calculations. V1 plus V2. When we add these things, as long as we're in what's called a flat space, which you guys will always be in for quite some time, what we can do to add them is just pick them up and scoot them around, as long as we don't change what? Their defining properties, which are their length and their directions. Don't turn them and don't stretch them. As long as you do that, then you can move them around and stick them tip to tail. So pick this guy up. For some reason, that always reminds me, you know, the little me characters on the Wii and their little feet kick. Pick it up. Woo! Pick him up. And move him over here. Okay. That's V1. I'm going to pick V2 up. Stick it over there. And so that would be the same as that. Simple. Now, if we wanted to do V1 minus V2, same sort of thing. Okay. So V1. Here's V2, except we're saying minus V2, which means plus the negative of V2. So that would be this. And that would be equal to this. Or what if we wanted to do that? Can we do that? What do you think multiplying a vector by 2 means? Stretch it. Add it to itself once, yeah. And multiply it by 2. So we could do that. So this is negative 2. So first I got to flip it. And then I want to double it. So that's this. Good. And then plus a half of that. That make it sound?
Yeah.
Definitely helps.
Yeah, it's sticking in my brain.
Good. That's what I want. Is it cool? That all making sense? Pretty straightforward.
So curious what the application is for vectors.
Everything.
Yeah.
So let me give you some, that's a good question. I'm glad you asked it. So we're getting a little abstract here. So forces are vectors. When we write Newton's law, we write F equals ma. So forces along some direction produce accelerations along that direction. Electric and magnetic fields have both magnitudes and directionality. You use a compass, right? Compass is telling you the direction of the magnetic field, but you could also imagine a device that tells you how strong the magnetic field is. So these things have directionality. And the presence of the directionality of the electric and magnetic fields tells us something about the forces, which are vectors, that those fields place onto charged particles, which are in the presence of or moving through those fields. Angular momentum, rotation, has a rotation axis that's a vector. Yeah, to be more precise, that's what's called a pseudovector, but it's not important to point out. Same thing for magnetic field. So they're all over the place. We're describing things in a three-dimensional world, and we need to know about displacements and velocities and accelerations and forces and rotations and fields which exist in that three-dimensional space that have orientation. So where does it appear? Everywhere. Everything we're going to do involves
Sound effects ever?
yes, of course.
In the middle of the test.
I was about to say, they're gonna hear it.
Yeah.
It's like, one time.
That's right. Now, in addition to your sound effects, you're also going to be learning some hand signals. We're going to start doing that before too long. In just a little bit here, we're going to introduce what's called the right-hand rule. And the right-hand rule kind of goes like that. You always use your right hand, though. It's very, very important. So you'll be making some hand signs as well. So, now, we've talked about adding and subtracting vectors. Those have very intuitive meanings. You know, I suspect if I left you to think about it for a little bit and I had a couple arrows and I told you to add those arrows, especially if you started thinking about them as displacements, you probably would know what adding those vectors meant to be thought about. The next thing I want to ask you is, what about multiplying vectors? Now, well, you say, well, didn't we do that? Well, not really. We multiplied a vector times a number. So when we multiplied the vector by a number, we stretched or contracted its magnitude. What if you multiply two vectors? Well, each of them has a magnitude. Each of them has a direction. Is it even obvious what that means? I think it's not obvious what that means. It's certainly much less obvious where that is useful. But again, I can give you some examples. For example, the magnetic force on a charged particle only exists if that charged particle is moving. Now, electric fields will put a force on a charged particle no matter what. But magnetic fields, say there's a magnetic field, as long as you're sitting still, the magnetic field doesn't notice you. You don't notice it. As soon as you start moving, then you've got your velocity, which is a vector, and you've got the magnetic field, which is some other vector, and the combination of those two vectors is going to result in a force on you, which is also a vector. Which leads us to sort of an interesting question. If you multiply a vector times a vector, what type of object do you get? Well, the example I just gave you, you ended up with a vector related to the force. Charge times velocity cross, we'll call it magnetic field, is the force on a charged particle. Is it obvious that a vector times a vector should be a vector?
Well, it should be, logically. I don't know.
Should is a very loaded word.
I don't know about obvious.
It's not obvious, and it's not even true.
Okay. That makes me feel bad.
It is true that that's one sensible way to define it. We're going to talk about multiple vector products. In fact, there are at least three of them that make a whole lot of sense. And what's going to maybe surprise you a little bit, and what's maybe going to be a little bit of a deviation from the way that you've historically thought about mathematics, is I'm going to suggest to you that when we multiply two vectors, we get to, not only get to, but have to make up and decide and choose what that means. Is that pretty powerful? How do I get to choose? It's math. Well, you define what the rules of the mathematics are that you're using. You have axioms. You define the structure of the mathematics you're using. You have to make sure, obviously, that the construction that you're defining is consistent. It has to be consistent, self-consistent. And it would be really nice if the thing that you were defining was also useful. But what I want to do for the next little bit, and we'll just kind of set the groundwork here today before we wrap up, and then this will be our major effort for Monday, is I'm going to think about what it could even mean to multiply vectors together. So one possibility which we've hit on is vector times vector gives me another vector. That's a possibility. We're going to call that the cross product down the road for reasons that maybe become more clear. Well, what is the thing that's not a vector? We haven't used this word yet, but you may have heard it somewhere, for things that don't have directionality but only magnitudes.
Right.
Yeah. Well, speed is to velocity in the relationship that I'm trying to describe. So velocity, more technically defined, is how fast you're going and in what direction you're headed. Speed is just how fast am I going. It doesn't care about direction. So that's a good example. That's really getting us warm. But what do you know the name for those types of things that have magnitudes on them?
Sure.
I bet you've heard it. It's called a scalar.
Yeah,
Heard
it's
that?
Scalar.
Scalar. Okay. So we want to ask ourselves, what do you get when you multiply vector times vector? I'm going to suggest to you, that there are possible answers within the range of well-defined mathematical objects, right? In fact, one possibility is a scalar. Vector times vector equals scalar. We'll call that the scalar product. We'll also call it the dot product. What's another possibility? Vector times vector equals vector. We'll call that the vector product. Is that surprising? We'll also call it, remember the other word I said? We'll also call it the cross product. We'll have a different notation. Another possibility, which we're not really going to hit on much in here, maybe in a few cases, is vector times vector equals matrix. We'll call it the outer product.
The what?
Outer product. So inner product we'll call the dot product, another name for that, and outer product will be vector times vector gives matrix. We won't worry about that a whole lot. But what we're going to have to get serious about on Monday, when we start to brainstorm a little bit about what possible consistent definitions could be, is what it really means to be a scalar, and what it really means above and beyond magnitude and direction to be a vector. I want to leave you for this weekend just with the notion of scalar. Most importantly, scalar means doesn't change under rotation. Doesn't change when I rotate it. And something that has a direction, if I rotate, you can tell the difference, right? But scalar doesn't change when you rotate it. For example, temperature is a scalar. Energy is a scalar under rotations.
What about gravity?
Well, gravity is a force, so a force will have a direction. So that makes it
Even in, what about space? There's like no direction.
well,
But gravity changes with rotation,
the directionality of a gravitational force, the fact that it pulls in a certain direction means that it is a vector.
Okay.
So, for example, if you
Yeah.
does that make sense?
Yes.
So the number one thing about a scalar, it doesn't have any directionality, so it doesn't react to rotation, like temperature, and like energy under rotations. Okay, so we will pick up with that on Monday. I think you have for me some test corrections and some book comments. So let's.
Test correction.
I did not know.
Oh, that's not what I meant. Not test corrections, but
Reflection.
test reflections. Test reflections, sorry. The corrections would be a very good idea, but I won't specifically collect them, but I do highly suggest that you do. That's not a good idea. You're gonna see if you can reconstruct the ashes. Okay, have a great weekend, guys.
What about triangle?
Oh, you can hold on to that. I'm going to give you a little bit of an enlarged set to go with that. I haven't figured it out yet. So if you've got those done, that's fantastic. We'll hand them in with some additional problems next week.